Russia is considering a temporary disconnect from the World Wide Web to test cybersecurity.
The sun produces more energy than we can comprehend. Its core reaches a predicted temperature of 15 million degrees Celsius, or roughly the same temperature as an exploding hydrogen bomb.
So there are only 4 simple pieces to our genetic code, right? Cytosine, guanine, adenine, and thymine, C, G, A, and T. Well, not anymore, folks, not anymore. Now, there are 6. When you actually think about it, trying to make an entire complex being and all the crazy stuff that goes with us out of only 4 simple pieces isn't very efficient. The proteins that our DNA codes for are themselves made out of amino acids, of which there are only 20. Isn't that crazy? Every living thing is made out of different combinations of the same 20 basic building blocks, coded by just 4 even more basic building blocks. So it's safe to say scientists have been dreaming about expanding that toolkit for a long time. And that's right, we've upgraded. These unnatural additions to genetic code have names like this and this. But to simplify things, we call them X and Y. And this class of synthetic DNA base pairs are called xenonucleic acids, or XNA. Biochemists first started trying to add these new base pairs to DNA in the 1980s, which, as you can imagine, is not easy. Base pair bonding in natural DNA is highly accurate. A always bonds with T and C always bonds with G, but the pairs we've added are a little harder to get right. It's easy for these newbies to mispair. This is because the hydrogen bonds that hold the 2 sides of a DNA helix together are really weak. And while they're enough for the natural stuff, holding synthetically introduced base pairs together properly requires something a little stronger. One team has gotten around this bonding problem by making the new base pairs stick together because they're both hydrophobic, making them line up properly to bond in an effective way. Others have simply tried to strengthen the hydrogen bonds by manipulating the structure of the unnatural bases. But that's really just the first hurdle. Once you've gotten the new base pairs to stick together, you have to make sure they don't disrupt the rest of the DNA and make chunks of it non-functional. And then you have to get the cells of whatever organism you're adding it to actually accept them, and to be equipped to produce whatever these new bases are asking them to produce, which seems like a pretty big headache. Nature is just doing fine on its own, a master technician with all its gorgeous cellular machinery, so why do we want to mess with it so much? Well, because it's worth it. We already genetically engineer organisms like E. coli to produce a desired chemical product for us. Because their genome is easy to infiltrate and they reproduce so fast, you can make industrial quantities of the thing you want, like insulin, for example. But as we've discussed, we're only working with 20 amino acids to build everything out of. Adding in synthetic base pairs could make it possible for organisms to be able to build proteins out of more unusual materials, like synthetically produced amino acids, maybe metal-binding ones that would be conductive or magnetic, making biomaterials that could be used in electronics. Okay, but are we getting into mutant superhero territory here? Well, it's easy to want to make that leap, but we're not quite there. Because all of these materials are synthetic, both the base pairs and any unnatural amino acids those base pairs would code an organism to use, they're obviously not found in nature. Scientists have to provide these materials to the organisms in order for the organisms to be able to use them, and in most cases, even to survive. If the modified organism doesn't have the materials to make these synthetic base pairs, they just die. They couldn't run rogue Jurassic Park style even if they wanted to. Realistically, we'll use these new capabilities to